All right, good evening, everybody. Welcome to the East Valley Astronomy Club meeting for tonight. Let's see, you've all seen what's up there already, so let's go ahead and just continue on here a bit. Normal welcome slide that we always do every month we're here together. So for those here in the room and for those that have joined via Zoom that Tom over here is handling, we want to thank you for being here tonight. And as always, I've been saying this for over a year now. We hope you enjoy yourselves tonight. We hope you learn something interesting. You're going to learn about M31 and all about asteroids tonight. We hope you make a new friend. That's very important. Meet somebody new. Develop a new friendship. And we hope you reconnect with old friends as well. So we're thankful you're here. First of all, cell phone reminder. If you haven't got your phone off or on vibrate, do so now. I do the same thing I'm asking you to do right now. So. All right, so next up, any visitors tonight? So we'd like to meet you just ever so briefly. If you have, you raise your hand and introduce yourself if you'd like to do so. And Amanda, you're on. So.
There, I'm Bob Austin. I just joined the club last month. I went to one of your star parties next door. I was president of the San Diego Astronomy Association from 2006 to 2010. Moved here in 2020. I sold all my astronomy gear in 2011. And when the comet came in December, it kind of relit the fire. And I bought one of the little black boxes over there. So here to meet some fellow astronomers.
Okay, well, welcome. Glad to have you here tonight. Anybody else? One back over there behind you.
Hi, I'm Rich Jacobs. I used to belong a long time ago, and about 10 years ago, retired from astrophotography and astronomy, and then I was reinfected about a year ago and getting back in. So, and I just joined last month again. So it's good to be back.
Yeah, well, welcome. Glad to have you as well. Anybody else like to introduce yourselves? Oh, we got a couple more over here.
Hello, everyone. Good evening. I'm Hoyt Slocum. I'm a new member to the group, and this is my first in-person meeting. I brought my adult supervision, Michelle, with me tonight. She didn't know we were coming. She's on a mystery Friday night date night, and this is where we ended up. So, new to the club. I run a CPC 8 with a bunch of new gear that I would like to improve my skills and learn from people with more experience. And we're also interested in outreach with young people where STEM disciplines are concerned. So thanks for having me tonight. Great to be a part of the group. Nice to meet everybody. Look forward to meeting you.
Thank you, Hoyt and Michelle. Anybody else? Hands up.
Hi, I am Jason Bro, and I've been once before, but it's been a few years. So my wife keeps telling me, you gotta go. So finally I'm here. I do visual astronomy. I haven't gotten into photography at all yet. Mostly self-taught and don't get out enough. So hopefully that'll change too. Thank you.
All right, thank you. Anyone else here? Any other hands? Okay, I think that's it. And Ed in the back corner. If you could kind of make sure we have enough chairs if people come in, I'd appreciate that. All right, thanks. Gordon's got a couple there, so thank you. All right, well, thank you to our new visitors here. We're glad to have you actually here tonight. And if you're somebody that's been around for a while, hunt down a new visitor during the break and say hi, please. All right, tonight's agenda. So we have our normal announcements. We have our general announcements that I do every month. So I could probably have one of you come up here as a guest presenter and go through those slides because you've seen them now 12, 13 times. We're going to talk a little bit about public outreach tonight. So our events coordinator, Alice, will be taking those slides from me. And then we're going to talk about some potential club activities. And I'm going to take some straw polls in here with raises of hands, or hands raised, I should say. We have a member presentation tonight from Mike Wiles. As you can see, he's going to talk a little bit about M31, something different there. At that point, we'll take our 7th inning stretch for 10, 15 minutes, get refreshments, chit chat, get our main speaker ready to go and all that. And then we have our main speaker tonight, which is Tom Polakis, and he'll talk all about asteroids, everything you ever want to know about asteroids. Matter of fact, when Tom's done tonight, we're just going to land all the satellites, shut all the satellite research facilities, because we'll know everything there is to know about asteroids when Tom's done tonight. So anyway, all right, so that's tonight's agenda. All right, general announcements. These I do every month, so you'll recognize these. So it is that time of year again. So it is February, so it is a new year. So if you'd like to join or renew your membership, now would be a good time to do so. Membership's helpful because it pays the bills, it keeps the lights on, all that good stuff. There's multiple ways to join. You can do so via email, you can do it online, you can mail a check in through the snail mail, regular or post office mail. You can send us stuff through PayPal, or you can see Brooks at the back table back there and just do it right here in person live tonight. FYI, you'll see PayPal up there on the screen. That may have to change soon. Brooks and I have been talking for about a week now, and we're trying to get Zelle hooked up so we can start using Zelle as a way of paying as well. If you're not familiar with Zelle, probably a lot of you are. It's built into most of the banking apps these days. It's just a big thing that all the banks got together and did. And so it's just a free way to transfer money around from checking account to checking account. So we're looking at Zelle as well for that. In addition, if you click on the new member guide link, which was, let me back up one, you'll see the new member guide link there. It's kind of on the right-hand side of the slide on the web page as well. You get the new member guide, tells you a little bit of what it is to be a member. If you'd like to know what's happening here, there's at least 4 different ways you can find out. Number one, you can always subscribe to our email distribution list. And as always, we never send those email addresses anywhere else, so you don't get spam from 30 other companies by signing up with us. And you'll probably get about roughly 6 emails a month from us. There's usually 3 emails that go out to kind of reminders for this meeting. Then there's an email that goes out occasionally that advertises something special event. Like I sent a couple of them this month advertising some special events that were coming up. So usually it's about 6 emails a month, so it's not a whole lot. But if you still don't want emails pushed at you, you can always pull information manually yourself by going out to our webpage. You go out to the events and meetings tab on our webpage. It brings up the calendar there. And as you can see on the calendar, let me use this little laser pointer right here. You can see there's actually things happening on these days. And if you click on any one of these little events, it opens up a separate window. It shows you what it is, where it is, what time it is, gives you all the details, addresses, things like that. So there's another way you can find out what's happening here. You can also use our newsletter. So our newsletter has information in it as well. If you signed up for our distribution email, you will get the newsletter automatically. That'll be one of the emails that'll come in each month. You can always go to our website here as well and manually pull out the current newsletter, or probably any newsletter in the last 5 years or so. They're all out there. So you see lots of newsletters. And then lastly, there's a Facebook page. So we do have an East Valley Astronomy Club Facebook page, and you're able to go ahead and join that. And it's just a normal Facebook page. You'll see, hey, anybody going out to pick up posts this weekend and like to go along? Or, hey, I just took this cool picture of, M whatever, some messy object. Or I have a telescope I'm selling or whatever. So it's just a normal Facebook page, but you can join that as well. So lots of different ways to stay sort of up to date on what's happening here at EVAC. If you need equipment, we also make that available to you as well. Gordon and Alice over there brought in all sorts of equipment tonight. It's completely free. Take it home with you tonight. No. So anyway, no, we have used equipment for sale. So you can click on that. James, where are you at? There's James with a hand up. James handles all that. He's our properties manager. And so James has a separate website that button will take you to, where he lists all the things that are for sale. Most everything there is about half price, roughly. And so if you want to buy something and you don't have quite the bucks for something brand new, James does a pretty good job of checking them out and refurbing them when he can, and reselling a lot of used equipment there. We also have equipment for rent, as you see there as well. And so that's kind of a try before you buy kind of thing. And the rental prices are very inexpensive. We have manual telescopes, like push-to-go telescopes. There's a actual go-to scope out there. We have filter kits. There's a number of different things out there that you can rent. So before you buy it, you want to try it, you can rent it for a couple of weeks and see if you like it or not before you buy it. So that's available to you as well. Do you need more knowledge? Would you like to know more about astronomy? Out there on our webpage as well, underneath News and Resources tab, there is a virtual beginners lab. Those little blue boxes there that are cut off, there's actually 33 of those on the webpage. Each one brings up a little topic that tells you more about that particular topic. In addition, we also run live classes, once again through James, who just does our properties management as well. And actually, you just started a class. It's what, about 2 weeks in right now, or a weekend? Okay. 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 All right, good. All right. So anyway, like I said, there's class going. And you can see the email. If you just email properties@evaconline.org, that'll go to James as our properties manager and ask about classes if you're interested in doing that. He does have 2 classes, a basic telescope class, and then the other one is, as you can see there, is a planetary astrophotography class as well. So it's 2 different classes that he does offer. So it's a lot of fun. I've dropped in on the class at least twice, and everybody seems like they're having a great time. So they seem to really be enjoying it. Anyway, Alice, you can start making your way over here. So one of our charters is giving back to our community. And so Alice here is our events coordinator for this year. And she's going to go through the next few slides.
Hello, everybody. Again, like Stu said, my name's Alice. I am the club's event and outreach coordinator. So we have 2 great opportunities with this club to give back to the community. And I believe giving back of your time and talent is probably the best gift that you can give. Oops, wrong way. There we go. So our number 1 way of giving back is right down this way, down the sidewalk, and that is the Gilbert Observatory at Greco. So they are open, or we are open, every Friday, Saturday night from sundown until 9:30. And as a volunteer, you would contact Claude, who's the manager, at the email address down below and let him know you're interested. He would get with you and let you know what sort of vetting, what sort of training would be involved. Myself and my partner, Gordon, over there, we typically volunteer twice a month. And I do not operate the telescope because I've not been trained, but I do entertain. That's what I enjoy doing. And I entertain everybody who's waiting in line, let them know what they're viewing, how to view through a telescope, and a little bit of astronomy 101. So it's really fun. You get to know members, you get to know guests. I highly recommend it. You also get to choose what days and how many days you want to volunteer. Our next available way to give back is through public outreach events, schools, HOAs, that kind of thing. Typically, it's about 2 to 3 hours of your time. And we also do the Second Friday Star Party. If you're interested in volunteering, definitely sign up at the free list, EVAC Outreach. That's the first thing you need to do. You do need to be a member. Sign up on that because we do all of our announcements, cancellations, updates, reminders via email. If you want to know what's coming up, just like Steve pointed out, go to events and meetings on our website and it's on the calendar. Click on the date and you'll see what is coming up. What do you do at these events? You share your love of astronomy with all of our guests. Now, this could be with a telescope or without a telescope. We just started. I had 3 volunteers, member volunteers, who showed up at a couple of our events that didn't have a telescope and helped educate the crowd, keep the kids in line, get guests to shorter lines, and it helped out immensely. All right. So I'm just going to share some of the past events. This was at CTA Goodman Elementary School, and a shout out to Rick and Becky and Andrea for helping out. They were our non-telescope volunteers. They were amazing, keeping the kids under control, and some of the parents too, but everybody had a blast. This was Steve's HOA star party. This was great. The number one question I kept receiving from guests was, why are you guys here? And I said, your neighbor, who happens to be the president of our club, wanted to share the sky with you. They loved that. They were very, very appreciative. They loved, we kind of did a planet parade. Each of our telescopes were on different planets. So that was a huge hit. This was my favorite star party because we were the rock stars. The kids absolutely loved this. There were 256 guests at this party. It was also the first time that we had our little meteorite display. Brooks was kind enough to offer to man that. There was a line just as long as that meteorite display as there was for viewing through the telescopes. These guys loved us so much. We were up on the marquee. I received a very nice thank you email to our club for us showing up and giving our time and talent to the kids, to the parents, and to the teachers. And this one, American Leadership Academy, that was for our fellow member, Josh. It was for his third graders, part of a science curriculum night. We were it. Again, a blast. Meteorite was a huge hit to the table. The telescopes, the same thing. It was a little iffy if it was going to happen because of the weather, but Mother Nature cooperated and we were able to do it. Our second Friday star party, there's no pic because unfortunately I canceled it because the weather was a little iffy and there was water in the sky. All right, here are upcoming star party events. I'm not really going to go over them individually because you can look those up on events and meetings on our website. And then last but not least, I have my two S50 and S30 Sea Stars on display over there for all of you to come over, take a look at and share. I've had the S50 for about 1.5 years now, the S30 for about 2 weeks. So next month I will do a member presentation and let you know which one that I like the best. And last but not least, I want to do a shout out thank you to all the volunteers that have helped so far and who have confirmed with me about helping on the parties coming up. I could not do this without your help. So thank you very much.
Thank you, Alice. Appreciate that. All right, let's continue on here. Club activities, a few things here to just talk about for just a moment. So I sent a couple of these first two things out in the to the distribution email alias just in the last couple of weeks. So the 2025 Messier Marathon is coming up. It's 2 nights. And as you can see, it's going to be Friday and Saturday night, March 28 and 29. And it will be out at the normal place we've been going for several years now, out at Hoveder Road. So out I-10, almost to Quartzsite out there. If you've never been out there, it's, you know, it's about a 2-hour drive or so, 2.5, something like that. But it's really dark out there and really nice. So I like it out there a lot. So it's a lot of fun. You could do the marathon either night or both nights if you'd like to. But it is Saturday when most of the other additional things are happening. This particular event is not actually our event. It's actually done by the Saguaro Club, but they always invite us and we always go along, so it should be a lot of fun. I'm actually going to go on Friday myself because I can't go on Saturday because I actually have 2 things happening that weekend. The other thing that's happening that weekend, this is on Saturday night, is Fountain Hills is having their annual Fountain Hills Dark Sky Festival. And so several of us are going out there with telescopes to support them. We've done that for a few years now. They're wonderful out there. It's a lot of fun. And there's actually not several hundred people that go to this event. There's several thousand people that go to this event. So it's quite large. I mean, they have an astronaut out there you can talk to and ask questions. There's all sorts of things going on out there. So it's a lot of fun. And matter of fact, some of us will be out there at 4 o'clock before, well, a little bit before sundown even, so that we can set up our solar scopes that actually people can look at the sun through solar scopes as well. So that's available to you. Once again, it's the same weekend as the Messier. You can choose one or the other or both or neither, but you have options is what you have. Now, when it comes to club activities, I'm going to do a little bit of a straw poll here with the raising of hands here for just a moment. In the board meetings, we've been talking about other things to do as a club, just to make it more social. We're a social club, so let's be social, right? So anyway, so some ideas for additional club activities, and once again, we just sort of like to gauge some level of interest here. So one of them is down at the University of Arizona in Phoenix, or not Phoenix, in Tucson, underneath literally their stadium down there, there is a mirror fabrication lab. And I'm not talking about little mirrors that fit in your Celestron or your Orion or your Meade, the old 8-inch mirror. We're talking like 100-foot diameter mirrors, big mirrors that go in, big professional observatories around the world. So they do run tours down there. It's $25 for approximately to get in. We have considered renting some sort of a shuttle bus to take people down there. But the max they can take at any one time is 15 people through the lab. So it's about an hour and a half. So what we're thinking about is taking a max of 30 if we have that many people interested, and maybe doing half go through while the other half are doing something else, and then we switch, and then when we're all done, we basically head back up here to the Phoenix Valley area. So if we were to set up, before I spend any more time on this, because my time is limited, I still got my day job. So anyway, how many might be interested in touring a mirror lab? Would that be something people would be interested in? Okay, it looks like we have enough, plus whatever's out on Zoom and people who aren't here. Okay, I'll pursue that a little bit more fully then over the next few weeks, and we'll try to get something set up. Another idea that we've had for something to do, of course, would be a trip up to the new Discovery Center at Lowell in Flagstaff. If you're not aware, Flagstaff opened up a brand new Discovery Center, kind of a new visitor center, just in the last several months. It's quite lovely. I saw it while it was under construction. I went up and met a guy named Kevin up there, works up there, and he kind of showed me around a bit. It's actually quite nice. In fact, the whole top is open on this building, and they have heated chairs that lean back and look at the sky, and they actually have a live like planetarium show where it's not projected onto a ceiling. It's actually, they're pointing out whatever's in the live sky. So we thought about doing something like that. If we were to set up a trip like that, how many might be interested in touring that as a group? So quite a few here. Okay, so no interest there. I got it. So anyway, okay, I'll pursue that a bit as well. I'll give Kevin a call. Another thing we could do, now this is smaller groups. As you can see, we can only do a group of 10, although we can maybe do multiple weekends if we want to set it up. But out at Mount Graham, if you're not familiar with Mount Graham, it's out on the east border of Arizona. It's by Safford. Mount Graham is right above Safford. They actually have 3 telescopes up there. So they have a radio telescope that was involved in imaging the first black hole, and you tour that one. The Vatican telescopes up there, you tour that one, and then the large binary telescopes up there as well. And the reason it's limited as 10 is the only way you can get there is you have to drive up in a van with a driver, a guide, and 10 other people. And it's a pretty long day. The tour, as you can see, starts at 8:30 in Safford. You wind your way up the mountain, you do the tour, and then you wind your way back down the mountain, which takes an hour up and down the mountain. It's all switchbacks, but it's actually fascinating. I did it with one of the other members in our club last summer. We camped up there actually for a couple of days, took our telescopes, wonderful black sky, and but then we toured the telescopes one day as well. So if anybody interested in doing something like that, like I said, a long day, so enough. So we might try to set up a couple of weekends. Okay, I will spend some time and try to pursue that and try to flesh something out. And then as a board, we'll decide what we can and can't do. So anyway, all right, thank you for that. I appreciate the straw polls. Member presentations. So we have one member presentation tonight. So the presentation is from Mike Wiles here. It's M31, something different. If you want to come on up, Mike, and we'll give you the mic.
All right. All right. Hello, everybody. M31, something different. So this is an image I took of M31 with my telescope. You may be looking at it thinking, what's different about this? Mostly it's that it's not completely color and oversaturated is one piece of it, but the point of taking the images of M31 for me was less about getting a pretty picture of it and studying something that's actually in M31. As in here, like if I zoom in here, this little triangle of stars, this little triangle of stars towards the middle here, and that one that's highlighted under the yellow bars, I wanted to study that star for one simple reason. That star is famous because of this hippie looking guy right here in 1925 used that star to determine that the Andromeda Galaxy is not within the Milky Way galaxy. It's actually an entire island universe. And that changed, as you know, our entire theory of the universe. And he's actually named after the telescope, Edwin Hubble. So in his observations, he was looking for novae, doing surveys looking for novae. And he noticed going back on plates that one of the stars labeled in the upper right corner there with VAR was not a nova, it was actually variable. And he marked that star, and you'll notice it's a lot fainter here. You'll notice that same sort of triangle that was in my image. So he, piggybacking on the research of this lovely woman, Henrietta Swan Leavitt, in 1908, Henrietta Swan was surveying Cepheid variables in the Small Magellanic Cloud. And she realized these Cepheid variables have a very specific period. But knowing that they're all in the Small Magellanic Cloud, she made the assumption that they're all relatively the same distance away. And if they're the same distance away, then she can learn something about them. And what she learned is that there was a direct relationship between the period, how long it took to get bright and dim for those stars, and how bright the star actually was. And she was the first person to posit that we could use that to tell how far away something was. And so Hubble basically took her research and built upon it to figure out how far away M31 was. Long story short, the something different part of this for me was I read an article online. It was published in Astronomy Magazine a few years ago that talked about, could we recreate Hubble's experiment with a 100-inch telescope with modern amateur equipment? And so that's what I set out to do, to see if I could recreate his experiment using my own equipment that cost much less than that 100-inch telescope on Mount Wilson did. So I have, this is my observatory down in southeastern Arizona. I have a 14-inch telescope in it, standard CMOS camera, and I started a series taking 5-minute exposures, imaging basically every clear night, and then stacking 6 to 12 exposures, because while that star looked sort of bright on my image, it is not. So having done that, basically this is a GIF that flashes back and forth. The red square is circling the star that we're imaging, and like here was faint, here was bright, here was faint, here was bright, here was faint. Like that's the data that we were dealing with in this. And so it really is at the limit of the telescope. But what I would do is I would stack 6 to 12 exposures so that the star would be bright enough to actually measure. And then with photometry software, I would take that and compare it to these. You see the 4 green boxes, those are stars of known brightness. And so I can measure how much this star changes in relation to those to figure out how bright the star is. And it changes day after day after day, slowly. After a certain period of time, if you get enough data, you can then plot a light curve. You'll see that the pattern repeats. And in the case of this star, I figured out, I noticed that the pattern repeated after 31.34 days. So like Henrietta Swan Leavitt posited, if I know its period, 31.34 days, I now know enough information about this star to figure out how far away the Andromeda Galaxy is. A little bit of statistics, some of this will be important in just a second. This star at its brightest is magnitude 18.4. At its dimmest was magnitude 19.75. It was barely visible in my telescope at its dimmest. Its average magnitude was 19.1. This is For those of you that aren't super familiar with the magnitude scale, if you go to a dark sky, you can probably see with your naked eye about a 6th magnitude star. So this is pretty far out there. So now that I have this light curve and this data, we get to the next part. How did Hubble calculate the distance? And there's some math here, but this is really simple math. It's surprisingly simple math for a guy that is credited for this experiment. We first apply Henrietta Leavitt's law that gives us the absolute magnitude of the object. We then use that with the distance modulus equation to figure out how far away it is in parsecs. And then because parsecs isn't in a totally arbitrary number that Americans are used to, we can convert it to light years by multiplying by 3.26. I won't make you do all the math. We are going to walk through it real quick. So my attempt using my data to see how close I could get to Hubble's answer was first to take this first equation, and it's basically multiplying the logarithm of that period, 31.34 days, times -2.11 and then subtracting 0.6. This is from Henrietta Swan's period luminosity relationship. I get an absolute magnitude of -3.76, which I know is, I'm probably putting half of you to sleep by now, but it gets fun now. Then we use the distance modulus to figure out how far away it is. And I take that and I just plug my numbers in. This 18.46 in red numbers, it's red for a reason. One of the things that Edwin Hubble did when he did the math was he didn't use the average magnitude like Henrietta Swan had suggested. He used it at his brightest because the plates that he was measuring from had better signal, and so he wanted to use that. Well, if you use a magnitude that says the star is too bright, what's your answer going to be? It's going to say it's closer than it really is. So the reason I have it in red here is because I used my brightest magnitude to try to recreate his exact experiment. So having done that, doing that math out, the next thing I get is that the distance is 10 to the 5.44 power parsecs, which comes out to 275,000 and change. Multiply that by 3.26, and my answer was, trying to recreate Hubble's experiment, was 897,875 light years. In January of 1925, 100 years ago last month, he published at the AAS meeting that the Andromeda Galaxy was 900,000 light years away. And it was with amateur equipment. It's a dim object, but it was surprisingly simple to do, especially once you understood the math. And I'd love to take credit for this, but I can't because, like I said, it was an astronomy magazine article that I'll link here in a second. One of the other things, though, that comes from it is Hubble's answer was wrong. And we've learned a whole lot about M31 and how far away things are in these things since. So using the modern equation for the period luminosity relationship, how close could I get to the generally accepted modern distance? So running this whole thing through again, 31.34 days, I get an absolute magnitude of -5.22. If I then this time plug in the average magnitude of 19.1 rather than that 18.46, I will get an answer that's closer as well. So that gives me a distance of 10 to the 5.864 power, which is 731,000 parsecs and change. If I convert that to light years, I get an answer of 2.383 million light years away. The kind of accepted answer today is 2.53 million light years away. So this is interesting that my answer is a little further off than it was with Hubble's. And I started to wonder, why is that? I got 31.34 days when I did my observations. The actual period is 31.91 days. So that's why, because the period determines the distance, that's why my answer is slightly off. And the solution is, just like if you're taking regular pretty pictures of M31, more data, always more data. If I had more data, I likely would have gotten much closer to that answer. And then as I referenced, this is where I got this. I would love to say I had this awesome idea, but I did not. So it's from this article. If you go look online, it is there. It's a great write-up. Bernie, what's up?
Yeah, anyways, did you check to see what the period that Edwin Hubble got compared to what we know now?
Yes, but I don't remember what it was. He was
Was it
really,
really
he was
close?
really close to mine. It was
Okay.
like 31.41 or something like
All
that.
right.
Yeah.
Is this method immune to how much extinction is between you and the galaxy? So if you're looking like right along the galactic plane out and it's really dimmed, does that matter? Is it just the period is the only variable you need to get the distance?
Yeah, so it has to do with the period and then the relationship between the apparent magnitude and its absolute magnitude. So thinking through that, extinction in the way probably would skew the answer. Yeah, like material in the way would make it seem like it's further away than it actually is. Yeah, hi.
One of the things that I always encourage people is to not put six significant digits when you're doing a calculation like this. So because it's just doesn't make a lot of sense. So think about the errors and then put an answer, and I bet your answers are going to come within a significant digit.
I'm kind of interested on the collection of the data. Did you just do like 1 month or did you do 3 months? And did you have to worry about the VOON, and how did you calculate or deal with that?
So I ran through just over more than a month. I started back in October, but it didn't, like, I had some observatory issues that had me down for a while. So I had a little bit over a month of data, and part of what I struggled with was I had full moon right at the point of time that it was at its dimmest. And so it was just near impossible. Like I was stacking like 2 hours of data just to get enough star in there to even make a measurement on it. Yeah. So the end result of all of this is like, what did I achieve scientifically? Absolutely nothing other than being able to show that like with like Bob Buckheim talks about all the time, you can do real meaningful things with regular amateur equipment. Yeah. Hey.
Do the atmospheric conditions affect your measurement of the magnitude at all, or is that all come averaging out? Or?
It all averages out, but what it does do is it makes me have to look closer at the data each night, like because the size of the aperture that I would use to measure would change from one night to the next based on the seeing. All right, thanks everybody.
All right, everybody, we're going to be on a break here in just a moment. A couple things. I have been getting over the last maybe 2 months requests saying, hey, any more of the gray zippered EVAC logoed hoodies? And so I have created a sign up sheet right there. Amanda's going to be sort of manning it during the break here. You can put your name and your size, because we have to order at least 20 when we order. And we maybe won't sell 20 of them, but at least if we can sell 15 of the 20 and are all the right sizes, that would help a lot. So she's going to be over there kind of handling that during the break. So if you'd like a zippered hoodie, gray zippered hoodie, you can look at mine. A couple other people got them on tonight. David Perriot's got one on wherever he's sitting there over there. So anyway, you can take a look at that. Also, I did want to also thank Gordon and Alice for bringing in the display tables tonight and just setting that all up for us to look at. It's awesome that you guys did that tonight.
Thank you so much. Happy Friday, everybody. Our featured speaker tonight is a 48-year amateur astronomer, and he was actually at the first EVAC meeting ever. He's been giving us cool presentations ever since, and tonight Tom Polakis is going to tell us all about asteroids.
All right. Okay, all about asteroids. I could not come up with a more creative title than that. So here we go. I don't know, most people in this room are old enough to get this reference here, right? So, oh man, wait a minute. Oh, we've got the wrong one on here. It's close enough. This is the one I presented to the Saguaro Astronomy Club 2 weeks ago, but it's barely changed since then. Okay, so first of all, we want to define what an asteroid is. And it's just a small body orbiting the sun. As we all know, they call them minor planets. That's important. We're not going to get into in this talk what defines the size, where it stops being an asteroid and then becomes a dwarf planet. That was a big controversy back in the day. But the most important thing, and a lot of the focus of this talk, is that the angular size, how big is that asteroid in the sky, is if it's Ceres, the largest asteroid, at its closest to us, it's less than 1 arc second. So what 1 arc second means is you point at Jupiter, which is usually 45 to 50 arc seconds, and you watch a transiting satellite, and it's about 1 arc second. So these are all for our telescopes up to a point, are just going to be point sources. They're not going to have any diameter, any size, any hint of what they look like. So there's all these clever methods of figuring out how do they rotate, what's rotation period, what's the shape, what are they composed of. And I have familiarity with a lot of these topics. I'm real familiar with the photometry part of it, and kind of self-conscious about a couple of the others where I don't know quite so much. Here's the topics that I'm going to discover, and I'm not going to read these, but you'll see those as they come up, all the way up to near Earth objects and meteorites. So I'll start with discoveries. Way back in the 16th century, the genius Johann Kepler came up with these great laws that define planetary motion, and still do, and they're just so elegant. And he even, way back then in the 16th century, there he is saying that he places a planet, but that was what he said, was there has to be a planet between Mars and Jupiter. We just have this huge gap, and why does that happen? So later on, this was known as Bode's law, and now it's known more as the Bode-Titus law. So that also uses this equation in the upper left-hand corner of that illustration, and that exponent n is in yellow, and then I'm showing, so I'll do it this way, 0, 1, 2, 3, and 5. There's got to be something there, and it's the same problem. So there's where 4 is, and we now know that as the asteroid belt. But they didn't know that as the asteroid belt in 1766. They just kind of suspected something would be there. So in the late 18th century, right around this time, there were the celestial police, they called themselves, and there's 24 of them, and they're each taking a 15-degree arc of the sky, and we're going to survey that. Remember, this is way before photography and everything, and it's all got to be based on star positions and star catalogs and watching something that looks like a star move from night to night. So they were doing that, and Piazzi was not a member of that, and he was doing star cataloging, and he saw, man, now what's going on? Here's a star that's moving even systematically across the sky, and he's saying, well, I think that's a comet, but we don't know what that is exactly. It doesn't have a tail, it's not diffuse or anything. And it actually got lost, and then the next year, about a year later, there was some good math that was done to predict about where we think it's going to be, and then it was officially found, and kind of an orbit was actually determined for it. So then in the next 5 years, there's the big 4 asteroids, Ceres, Pallas, Vesta, and Juno. Those are all discovered in that period up to 1807. And then there's this long 38-year gap. And so this is the first of many plots in the presentation. And all it's showing is here's those first 4 discoveries. And then there's this huge gap where nothing gets discovered. Again, all before photography. And kind of the reason for that is we have these 4 asteroids that get up to 7th magnitude, and 9th magnitude is pretty challenging in the middle of the 1800s. That's still a big deal. I mean, you can see that in telescopes and everything, but before photography or imaging, that's what we were stuck with. So in 1890, I think it was, yeah, Max Wolf, prolific asteroid discoverer, found the first of his nearly 250 asteroids. So I write a lot of these papers for the Minor Planet Bulletin, and I always open with who discovered the asteroid. And it's Max Wolf and his protege, Carl Reinmouth at Heidelberg. That's how that plot looks so far, going up to 1900. And you can see with photography how it's starting to slope upward. And we'll see more of that. This real busy table just shows a sampling of Max Wolf's discoveries. And he really went to town on this, and that's when asteroid discovery took off. So this plot, now we're going to take it from 1900 to 1980. And I took this data source online and thought something's got to be wrong. You know, it's going up pretty fast. We're up to 2,000 asteroids. Why is there's this discontinuity? And it wasn't wrong. What happened was that in 11 nights, the number of asteroids was nearly doubled. The number of known asteroids went up to about 4,000. And that's the great Palomar Mountain 48-inch Schmidt telescope. And the 200-inch is a great instrument, but the 48-inch Schmidt telescope, which is still in use, repurposed, is maybe greater in a lot of ways as far as the discoveries that have been made with it and the science that's been done with it. And so you'll see similar kind of discontinuities, these step changes that happen as surveys come online. Now we have to expand the scale to go up to 1.2 million, which is about where we are right now. This goes up to 2022, I guess it is. Now you have surveys where the CCD camera comes into play around 2000, and you had linear, which was killing everybody for a while in New Mexico, and then the Catalina Sky Survey and Space Watch and NEAT and NEAR, so quite a few of those. And so here's the entire plot just to show how on a single scale what's happening in the last 25 years. So who knows if this is going to keep going vertical, but what's really happening, and I'll talk about this later, is that it's just smaller and smaller rocks are being found. I mean, more inconsequential asteroids. At what point does this just keep going to millions and millions? And now you're talking about rocks that are the size of an Isetta. You know, so what's happening now to discover asteroids? Mike showed a frame, and both of us do our photometry with this software called Tycho, done by Daniel Parrott. And so it's done now. It used to be that you had to examine, or at least have software examine frames to find something where you would stack the frames that shows an asteroid moving, and whether it's in a single night or from night to night. And in a busy field, like what I'm showing here, you can see that it's nearly impossible. What Daniel's software does is it's going to look at every possible orientation, and there could be thousands and thousands of those that the asteroid could be moving across the field, every possible way. And then it's going to find out by stacking on candidates, much like how Mike stacked on the variable star to bring the signal up, and it's going to be able to find asteroids. So now people with telescopes that are of the size that we have, I'll refer to J.F. Goot in Mississippi a couple times during his talk. He has a 14-inch telescope in Mississippi of all places, and he's finding asteroids that are 21st magnitude, discovering asteroids with this little telescope. And because of this Tycho tracker software, which has really revolutionized the way things are being done. So I'm going to show pie charts in this presentation. And here's the first example of a pie chart here. So, okay, not my work. It's just beautifully elegant, isn't it? I just want to stare at it. Okay, so here's a pie chart of numbered asteroid discoveries, just to show you who's doing what. So Space Watch, which is in Tucson, actually at Kitt Peak, has been great at this. Linear on Mauna Kea in Hawaii. And then we're in Arizona again with that black bar in the section of the pie chart. That's the Catalina Sky Survey. And then you'll recognize some of these as recent comets that we've had, Pan-STARRS, NEAT, WISE. So those are also discovering lots of asteroids. And then along the way, they find these comets such that amateur comet discoveries are pretty almost a thing of the past. They're still happening, but very rarely now. In this list is the Lonios, which was a telescope that Lowell Observatory ran on Anderson Mesa during the 90s and a little bit into the 2000s. And then that survey has stopped as well. That dome now has a 1 meter plane wave in it. So we've talked about discoveries and kind of how you find them. Let's talk about orbits very briefly. These are some of the orbits, Aitons and Apollos and Amors, but we just call that the asteroid belt. And some of these are actually in orbits that are perturbed enough that they come in and either intersect the Earth's orbit or they come fairly close. You go out farther than that and you have the Trojans in this figure. They're called Trojans and Greeks, but nobody really calls them that. They just call them Trojans on both those L4 and L5 Lagrange points in the orbit. So here's Jupiter, and these things will be preceding and trailing Jupiter all the time in that orbit because those are stable orbits. And remember, the solar system gravitationally consists of the sun and Jupiter, and then there's a bunch of other trivial stuff, but those are the real controlling forces in the solar system. So on yet another orbit, this is a near Earth orbit, and what we're going to also see here is from this figure, you can see that it's inclined to the plane of the Earth's orbit, and what I'll lead this into is a real basic description of what they call orbital elements. So orbital elements with these 5 elements, and I know I show a lot more on this slide, you can define the orbit accurately and it can run it forward decades or centuries and it'll still be accurate if you have enough data. And I put highlights around 3 of these numbers, which are those 3, and I'll show them in the next slide. So what's the eccentricity? It's just how oval is that asteroid's orbit. So perfectly circular will have an eccentricity of 0, and a parabola is 1, if you remember your conic sections from geometry. Then here's one that's fairly elliptical, fairly oval, 0.187. You also have the inclination, so you take the plane of the solar system of the Earth that defines that plane going around the sun, and you say, what's the angle to that? And then you want to know how big is that orbit, and that's just called the semi-major axis. You take that ellipse and you draw a line across the long axis, and it's half of that. And then from that, you'll get the period and the other stuff that you need to know. And now you can run free software out there called JPL Horizons, and you can type in any asteroid number and it'll give you down to the arc second, super precise. It'll give you its position anytime you want to know it. To get these orbital elements, you use what's called astrometry. And astrometry is just precise measurement of positions of objects on an image. So we call that plate solving sometimes. Astrometric solutions may be the more proper term since plates aren't involved anymore. And what that does is uses all these reference stars whose positions are very well known, and then you find out where's your asteroid. You can get that position using all of those real accurately. So you want to do this on, not on one night, you want to do this on multiple nights or even weeks to really define that arc. Otherwise, and this still happens today, asteroids are discovered that are right at the cutting edge and then they're lost for good. So it still is a thing that's happening despite all the methods getting so improved as they are. So I wanted to also know how bright an asteroid is. So, you see the word extrinsic that often, I can barely say it. So those factors are how far is the asteroid from the sun and how far is the asteroid from the Earth, and then also the phase. So the phase is just the same thing as the phase of a full moon. That would be 0 degrees. And I don't know if you know this, but the full moon, if you just plotted its brightness around full moon for like 2 days before, 1 day before, it really peaks when you get right to where that phase is about 0 degrees. And We see that also on the Earth. If you're up on a hill and you look out into a forest or even the desert, they call it the Heiligenschein, this really bright spot that's exactly opposite because you get these specular reflections. So that phase has a real big effect. And then intrinsic things are obviously the size, bigger is going to be brighter. And then these are my representations of Vesta and Pallas. So the albedo, how much does it reflect light? That comes, how much is, what's the reflectivity? So what I did was made this plot because I was wondering if you just did an idealized plot with asteroids that are at opposition, phase of 0, exactly opposite of the sun, and then you assume a couple things about the albedo. You don't need to know what G is, and what the plot shows you is as you look at the Earth distance, that gray band that's vertical is roughly where the asteroid belt is. So they're mostly going to be in that gray band, the ones that we're interested in. What's going to be the opposition magnitude? So 15, you'll be able to visually see that in a fairly large telescope at a dark site. 20, now we're getting down to the Mike Wiles range kind of thing that he does with his images. And then these are just a family of curves of the diameter of the asteroid, all very idealized. So I picked 2 asteroids just completely at random and plotted them. So there's my asteroid, which I actually, after Brian Skiff gave me this designation as a birthday present way back before I had any kind of camera or anything, and I went out with my 20-inch telescope and visually saw it was 16th magnitude at the time, 4078 Polakis, discovered in 1983, so it has a very low number. Dave Healy down in Sierra Vista, the late Dave Healy, was nice enough to give my wife Jennifer a designation. Her asteroid's just insignificant compared to mine. Sorry. Since she's not here to defend herself. So there's her asteroid, which peaks at about 20th magnitude. And we'll see images of that, believe it or not, later in the talk. So you just take one asteroid, and since I don't know anything about Python, but I'm pretty good at Excel, so I take everything and put it into Excel and plot it because I was an engineer. So here's the brightness of an asteroid that's in a pretty elliptical orbit, and this is what it does at opposition. These are 3 different oppositions, but because it's in this very oval orbit, there's what it does. Only reaches 17.8 magnitude, pretty faint, but sometimes it reaches 15th magnitude. And from this one, no, sorry, it was a couple prior to that, when it reached 15th magnitude, I had a pretty good light curve, some pretty good photometry from right here in the Valley of the Sun. I don't really want to go into this very much at all, but these are the 3 major types of asteroids. And this is one of my very weak subjects, so we'll just move on. So we go on to naming of asteroids, and this has been a lot of fun, and there's a lot of steps that go into the naming. So when they're first discovered, they're given a provisional designation. So it's just the year, and that GT, G is just the letter in the alphabet that represents the half month, so A and B are January, et cetera, and then T is going to be in that period when was the discovery made. So pretty, as the number of asteroid discoveries started to peak like this, now you have to have GT1, GT2, you have to have numbers added to them, and it turns into a real mess. But this is what they had for the asteroid, which eventually became Didymos, 1996 GT, which I have a particular interest in. Those are the 3 discovery images overlaid from the Spacewatch telescope, the 0.9 meter telescope at Kitt Peak. So after it's had that provisional designation, it eventually just gets a number. You saw 4078 attached to my asteroid. Eventually it got numbered 65803, and the discoverer then is allowed to give a name within certain guidelines. You're allowed to give a name. And back in the time that this was done, not 1996, but a little later, there weren't many binary asteroids known. So Didymos was the twin asteroid. They had found out that it was a binary, so it's kind of a clever name. Eventually, its companion was called Dimorphos. So here's some asteroid names then. So you have some great presidents and people who weren't president. And then you have artists ranging from the greats, Da Vinci or Jackson Pollock right down to Frank Zappa. And so you can read some of those. Douglas Adams, Hitchhiker's Guide to the Universe deserves an asteroid. Beethoven, Pink Floyd's got an asteroid, of course. And then you get into some local people or some names that we might know. Robert Burnham, the great Celestial Handbook, the late Gene Lucas, the late Randy Peterson did a lot for EVAC and SAC. There's Jennifer and me. Ron Greeley is a planetary geologist, very amateur friendly, and had a solid career at ASU. And then these two, which I really liked, All Even and All Odd. So yeah, so I don't know how they got away with that. Eventually, the cutesy names started to go away as they made it a little more restrictive. Now the subject that's near and dear to my heart, and I've done a whole talk here about photometry, and some of this is going to be redundant with that, but you get to see it again. So photometry is what Mike did. We just measure the brightness and color of things. We use different filters that are standard filters, and they're used B filter, V filter, I filter, and that's used everywhere so that you're on the same system or close. And so we just measure the brightness and we watch as an asteroid rotates, and it's a football shape or a potato shape. So when it's presented in its short dimension to us, it's faint, and long dimension, it's bright. And also, as it has craters or irregularities in the shape, those are going to cause little inflections in the light curve. So this is my photometry of a pretty bright asteroid. And you can see that after 7 clear nights, this is where, no matter how light polluted it is here in the valley, it's just great to be in Arizona because I can count on sometimes years getting 7 consecutive nights that are clear, which just wouldn't happen in Michigan or whatever. So you take that, and that's called a raw light curve for these 7 nights. And then you're going to use what's called a Fourier transform, and this is all done with software, and make that into a phased light curve. You're going to take all of that and find out where the repeating patterns are. So now you're showing a single light curve, and it's just going to keep repeating that pattern forever. And the software will tell you what the rotation period of the asteroid is. So in this case, it's about 30 hours. So that is a Fourier transform, and that's a Fourier transform. All right. So, all right. So I love these figures, these rotating diagrams. They just show you so much here. So this is called a faceted shape model. And what you would do is photometry while it's over here in the solar system, and then a couple of years later it comes to opposition, and then a couple of years later it does it again. So to really do this, to make one of these shape models, you need to observe it at several oppositions. It's a very ambitious effort. I've never successfully done one of these, but there's a site that'll show you the shape model rotating and what the light curve. So when you have something like the top asteroid, which we call a gray cue ball, that thing is either pole on, you're viewing it, so it's barely changing, or it's spherical. There won't be much amplitude to that light curve. It's barely going to vary in brightness. But then you have something that's like the bottom pane, and that's what I like because that's easy to measure and get a good rotation period out of. So here's my examples with my really simplified PowerPoint figures I created of a couple that are like what you saw on the previous slide. So you have a spherical thing. You still could extract a period, and I got to look close at that. Yeah, 0. So that's 6/100ths of a magnitude is all that variation is. But it matched the period in the literature, so it's good for something. So for my 15 minutes of fame in asteroid photometry, at one point in my little career there, I had the longest, slowest rotating asteroid, which took 75 days to make one rotation, not one day like the Earth. And once you find out that it's doing that, you only have to take like maybe half a dozen data points on each night. And I can do all sorts of other stuff. I'm not going to have to dedicate a lot of cadence to that because I know it's rotating really slow. So it gets easy, but again, you need a lot of clear nights. And this was an exceptionally clear period that we had for this. And it was a solid light curve. So it came out to 75 days. So I had this for like 2 or 3 months. I was all happy with myself. And then a paper came out in the Astronomical Journal in which a group that has done some data digging found 30 of them that were all way longer than this. And it's great. And they even cited my paper, which I was happy about. But what they had even postulated is that we will never know this, but you might have asteroids that take a year to rotate. And they're always going to go behind the sun during that period from our perspective because we don't have telescopes on the opposite side of the solar system. I wish we did for these types of things, or even 2/3 or a third of the way around. So some of these you're never going to really know, but there's no reason that they can't just keep getting longer and longer. So it's just kind of a cool thing. And another one of my little, not even a claim to fame, because now there are about 600 binary asteroids. So I discovered one binary asteroid with the photometry that you see here. I've highlighted with the blue oval over here, something weird happening, and I almost threw that data away, said, but it wasn't cloudy. So all right, I'll keep it. And then when I overlaid it on the rotation period, I was saying something's going on. So then I came out and anticipated on March 1st that there should be another one of these things happening. And sure enough, there's that V-shaped notch. And so all we're seeing in this case is we call them mutual events. So we're seeing when there's an occultation, the small body passes in front of the big one. Sorry, that's called an eclipse. And an occultation when the big one passes in front of the small one. So in the orbit, if it's inclined favorably to our line of sight, then you'll see the light curve, like my cartoon version of a light curve that you're seeing right here. And so overlaid on the rotation period are these little drops in light, these kind of V-shaped drops. And then you know you've discovered an asteroid. So with the help of Bob Stevens out in California, he was able to save me when it was cloudy in Arizona and get just the right additional night of data. We were able to figure out rotation and orbital period of these asteroids, which is pretty cool. And then it got featured on a Central Bureau telegram with the help of the great Peter Pravich, who knows more about this than anybody. And what I really liked about this is the name of the asteroid is 1803 Zwicky. It could have been anybody, but it was Fritz Zwicky. And that was just awesome because Fritz Zwicky was a very loose cannon among professional astronomers, great intuition. One of his famous quotes was that he called somebody a spherical bastard because he's a bastard no matter how you look at him. So, and so that just made this all the more rewarding. And I presented on this in California at a conference that Bob always tells this group about every year. And here's my scale model of about the size of the primary and the secondary. And conveniently, they're separated about the distance from downtown LA to where we have that conference in Ontario, which is pretty cool too. So yeah, so that's enough about binaries. Here's radar imaging. And it's a lot like just doing an ultrasound in a way, same principle. That's my grandson, Lincoln, who's 11 years old now. And here's the basics of radar imaging. So you want the thing to be nearby in order to bounce a radio signal off it. You don't do this with asteroids that are in the asteroid belt. You do it with near Earth objects. So you are measuring what the time delay is for the signal to come back, and you're measuring what's the Doppler frequency shift, and then polarization, which is, so I'm just reading from my charts now. And so in every other type of observing, you're using reflected light, but in this case, you can actually control that illumination, which is kind of different as well. And this has really advanced over the years, but consistent with this talk, I have to talk about the history of it. First of all, what we have as our two major radar imaging facilities, we had Arecibo and Goldstone, and that thing right there fell on the dish 5 years ago, when it was 2020, and so that'll never come back. That's the great Arecibo, which kind of sits in a natural crater in Puerto Rico. I think a couple people here have been to it, right, Bernie? Yeah, and unfortunately, that's not going to come back, and so they lost that. Still have the Goldstone radar, and it's still going strong. So the first time that a radar detection of an asteroid was made was Icarus. This was in 1968. It was just a detection, and this is just the article out of Sky and Telescope. Then there was a shape model made of 433 Eris, and so things are coming along in 1977, and now by 1989, they're making models which look like shape models of asteroids based on this. And then it gets even better still. So now you can make animated diagrams, and some of this is still sorcery to me, how they make this work, but now they're actually doing this sort of thing. And there's, like so many of these little sub hobbies, there's one person, currently the person is Lance Benner at JPL. Hope he's able to keep his job. Who's following this and is very amateur friendly, comes to the conferences and everything. There's Didymus and Dimorphos. I'll go past that fast. One that's at 3 lunar distances, so 750,000 miles away. That has this dumbbell shape, which is not uncommon among asteroids. So these things that are kind of fused together. And then just a few animations of rotating asteroids. So this is all, you can go out to the website, just search for radar imaging of asteroids, and you'll find a site at JPL that'll give you all this stuff. So obviously none of this is my original work, but it's another way that you're taking these things that are not resolvable. They can be like the school bus size thing that comes within half the distance to the moon, and that'll be a candidate, and you'll get this type of diagrams out of it. Another way, and this is done pretty heavily in Arizona, are occultations. So occultation, again, big thing passes in front of a small thing. I have an example here of a terrestrial occultation, and this was when they were going to demolish the Georgia Dome, which was where the Atlanta Falcons used to play. And there was a photographer all set up, just ready to go, and he had the video, and then this happened to him. So most of the audio for this would not be acceptable in this group. So yeah, anyway, so that's my terrestrial occultation, and here's the first successful asteroid occultation. I actually know the last guy on this list, Phil Dombrowski, from my 1.5 years spent in Connecticut. So what you're doing with an occultation then is you're going to watch the asteroid pass in front of a star, which in itself is amazing that can be predicted as accurately as it can. And different people are going to set up at different stations perpendicular to that path. And by seeing how long it disappears, you'll get a real good example or a good idea of what the size is across that chord that passed across the asteroid. So if that explanation made no sense, I'll show a couple figures here a little bit later. To do this, I had this slide all made up about here's the software and that kind of thing. And then I thought, I don't think he's at the meeting, but Wayne Thomas, you can easily get on his mailing list, puts out a great summary every month. He uses this software and what's online. And the summary is specific to Arizona, where you don't have to travel more than 50 or 100 miles to get underneath where that eclipse is happening or where the occultation is happening. And so that's probably better than talking about the software at any great length. The software will show you the path across the world, and then you zoom in and it'll show you a precise path. All of this has gotten way better in the last 5 to 10 years. And the main reason for that is, I talked about astrometry, about positions, is that the Gaia satellite, which was from the European Space Agency, has surveyed 2 billion stars. And it's one of the greatest accomplishments in astronomy ever that's been put into orbit that I put ahead of James Webb Space Telescope and Hubble Space Telescope for utility. And all it is positions and brightnesses and even spectra of these billions of stars. And now that that's so well known from an orbiting satellite with telescopes, now you can make these predictions better. This is just one example, but there are thousands of examples of how it's getting used professionally. So back to occultations after that little tangent. So telescopes and cameras, you can use a Dobsonian that's not even tracking the sky, and they call it pre-pointing. So you just point to this place and you set your video camera. That place has to be where the asteroid's going to go through your field of view, and the star is going to go through your field of view at the time that it happens. But it's being done. Of course, bigger telescopes better, as always, and you can use planetary video cameras. But the main organization behind this is the International Occultation Timing Association, and they sell a whole kit that's built for you. So I mentioned Wayne Thomas, but also now in Arizona, I think for the past 5 years, there's probably nobody more well-versed in occultations than David Dunham, who now lives in Fountain Hills. But way back when I was getting started in the hobby in the late 70s in Sky and Telescope, David Dunham would write in the January issue, would write the summary for the year and other articles about occultations when they're going to happen. And David's and his wife Joan, they're still going strong, and they're still posting on our local lists about stuff that's coming up. So here's a better version of what I was trying to do my hand waving explanation of. So this was a known binary, happens to be named after Arecibo, and these are paths. These paths going across the screen correspond to these observers. So what they're watching is the asteroid and its binary companion. See, this person with the yellow-orange path, that's the favorable path because that person got to see the occultation by the main body and by the secondary, by the orbiting moon of the asteroid. So, but just by having enough of these chords, and you can never have too many, then it starts getting better and better. So what this does is overlays asteroid occultation result on a shape model that was made from photometry. And now you start to, this is the best thing in science, is when you have 2 or 3 very different methods showing the same thing. And here's just an example of that. One of these spherical asteroids that would not be very favorable for photometry, and a whole bunch of chords. And these names, which are really small there, a lot of stuff from people that we may know in Arizona. So my buddy, J.F. Goot in Mississippi, he lived here, he joined SAC, he lived here for a year when he went to ASU, now he's a professor at Mississippi State in Starkville. He observes a lot of asteroid occultations, and what I want you to watch is that star, and I'm going to tell you when it goes out, and then it goes out again. And unequivocal, and even though he was doubted by somebody locally, he showed that he has discovered a binary asteroid. And then later on, there was photometry done on that asteroid that showed mutual events, and then it became no doubt. So pretty cool. Then he gets his name on an electronic telegram from the Central Bureau for Astronomical Telegrams, and eventually we know that that's another binary asteroid. And I think it's pretty special that he found this, because here's my table of how they were discovered, mostly through photometry, some by direct imaging. There's radar for these near-Earth objects, direct imaging, and only 8 stellar occultations that have been discovery of binary asteroids, and JF is one of them, which is great. Here's the methods that are used, and I just showed the slide. Now I'm pointing to 3 of them: photometry, direct imaging, and stellar occultation. And so that will lead into this slide. So here's direct imaging of 90 Antiope, which was found in 2000 with the Keck adaptive optics. system. Look at that scale bar, which is pretty ridiculous. That's 0.12 arc seconds separating the two bodies. So we knew that. And then there's this great stellar occultation result, which actually showed approximate shapes of both of the bodies. And then this is where I can say, look at me, look what I did. So then just recently, I went out and did photometry and showed very clearly when they're that steep, those are mutual events, occultation and eclipse. And you can even see the rotation are these arcs. So these little arcs that you see here, that's the rotation period, which in this case happens to be identical to the orbital period. And that's not real uncommon that you have synchronous orbits of asteroids. So I really liked putting this together because it just shows three very different methods of the same asteroid showing its binary nature. So we're back to plots again. First binary asteroid found in the early 90s, and now it's going up almost linearly. So we're up at around 600 of them that are known today. So I'm not going to talk too long about spacecraft visits, but here are some of them, some of the highlights. First time the first time humanity did a visit of an asteroid was 1991 Gasprin Ida, and that was a binary discovered by a satellite flyby or by a spacecraft flyby. And then there's these targeted missions. First time we did a sample return. And so there's Gasprin Ida shown very cleanly as binary near Shoemaker for 433 Eros. And this one's, the upper right pane is pretty cool. That's the sample return of the OSIRIS-REx mission, which had a lot to do, Arizona State had a lot to do. So this pod comes down, touches down and grabs some of the surface. And then a couple of years later, there it is sitting in a pod in Utah where it is touched down safely. And they're examining the contents, opening it up in the last frame. Ooh, this is really important. So now, again, very near to me. I don't know if this thing is going to play anymore. I'll try it one more time. Well, there we go. So this is Didymus and Dimorphos, and the point of this was to crash a spacecraft into the binary companion of an asteroid. And we're going to watch it happen here in slightly sped up motion, closer and closer, and it's just a direct hit, 5, 4, 3, as the countdown, until eventually you've destroyed the spacecraft, right, in the last frame. And the point of that was, let's hit it head on in its orbit. So you're having an orbiting moon going around on an asteroid, and let's hit it head on and see how much we can deflect it. And we'll know how much we can deflect it by how much we change its orbital period. And we can watch its orbital period by these mutual events with photometry. So I was fortunate to get hired a second time to work at Lowell Observatory to operate a 42-inch telescope that would observe this full nights of observing. And part of the reason they hired me is that nobody else wants to stay up till dawn observing. And you know, it's a 55-year-old telescope, and you kind of have to babysit it every hour or two. You can't ignore it and just let it rip because it's old and it has issues. But what we found then was the first thing that was really cool was that it had a tail that looked like a comet tail that was very persistent. It hung around for months and months until the asteroid was very far away. And you can also see the ejecta plume on this. This is my image from, is it 2 or 3 days after the impact? Because that's when I first got up there in early October. And here's the light curve. So light curve is looking very chaotic. And again, that's because these mutual events of eclipses and occultations are corrupting the rotation period. The rotation period is 2.6 hours, and the orbital period was 12 hours and 56 minutes, and it got reduced by 33 minutes. So this is the first time that we would get an idea of when the killer asteroid is coming straight for Phoenix, how much can we deflect it? So how much, if we send a spacecraft up there, and there's a lot of variables. People spent, many people spent the next year of their career or more doing studies from all the different ways this was measured. So our claim to fame at Lowell Observatory, this happened when the declination, how far south the asteroid was negative 31 degrees, I think it was, way into the southern sky. So it was all observatories in South Africa, Australia, and Chile. And we were the one northern observatory that got on the paper that went into Nature, which was cool. So right at our Lowell Observatory, and just by using this telescope that doesn't get used for many other things. So what's happening in the future? My favorite of these, now that I talked all about Didymus and Dimorphos and the DART mission. So Hera is going to visit next year. It's going to arrive at Didymus and Dimorphos, and it will be able to look at what does that crater look like that a spacecraft caused. That's fun science. Okay, finally, near Earth asteroids. So I talk about that a little bit. And so by definition, if it's perihelions less than 1.3 AU, we call it a near Earth object. So some of these don't really get that near. And then if it crosses our orbit, they call it a potentially hazardous asteroid if it's big. So one thing that's happened way back in 2011, we were already at 90% of the really big killer asteroids, ones that are larger than 1 kilometer. And just briefly, what this chart shows you is that you're looking here at asteroid size, big asteroids over here. They've been discovered. They've been cataloged. So that's what the orange curve is. But these asteroids, so 100 meters, 200 meters, there's a lot of those that are yet to be discovered. Maybe we're even halfway there. And Tunguska is way over here on the plot. So there's still a reason to be doing this survey and keep doing the survey if the budget doesn't get cut. So keep doing this and try to determine as many as possible. So in the news is 2024 YR4 or 2020, yeah, YR4 has now been determined that it had like a 2% chance of striking the Earth in 2032. And people who are not in the game or in this at all, the general public says, why can't you make up your mind? Now it's 1%, now it's 3%. It's because it's 23rd magnitude and it's way out in space, and we have to wait for the next approach in 2028. Then we'll really have its orbit characterized, and we'll be able to tell for sure if there's a chance that it can hit the Earth, which is still very small. I'll go past that one and this one. This is just telling you which surveys discovered asteroids. Way back in the 90s or in early 2000s, Linear was at top of the game. That was kind of a military program in New Mexico, just as a demonstrator more than anything. They also found a lot of comets. And then other surveys such as Spacewatch and that. Right now, the main ones that are discovering asteroids are Catalina Sky Survey and get this wrong here, yeah, Pan-STARRS, which is in Hawaii on Mauna Kea. So last part of the talk is about meteors and meteorites. There's actually discussion online about, so it becomes a meteorite when it's on the ground, right? It's a meteor when it's in the air and coming down, or all the way, its journey all the way to the ground, and then it hits the ground. But then there was this video that showed meteor striking the ground, becoming a meteorite and bouncing with loud popping sound very recently. So then the online discussion was, does it become a meteor again when it's in the air and then a meteorite? So, but yeah, so this is why you go on. This is why you go on social media, is to have these discussion arguments, people flaring up. So the Global Meteor Network is typically this kind of camera array shown on the right side. These things are really tiny cameras that are just a couple inches in size. And you have an array of them, 8 of them or something, pointing into different parts of the sky. And you have one, in this case, at the Lowell Discovery Telescope Auxiliary Building. It's that tiny, there's a little tiny dome this one is in. But there's amateurs that have these all over, one in Tucson, one in Prescott, and all over. And if you can get 2 or 3 observers to watch the same meteor come in, you can triangulate and figure out about where it landed, so you can find out. But you need multiple paths to have a good idea. And so that's been done successfully. And here's a case, before we really get into that, this was an image that I took when I was on the DART program, where my supervisor, Nick Moskovitz, told me, stop what you're doing because you only have a half hour to try to find this near Earth asteroid as it flies over. And it was really cruising, going, 20 arc seconds per second, which is really moving. So the position is also, the ephemeris is changing too. And it was a real challenge, but eventually that little dot right there is a little 1 meter, soon to be a meteorite. Unfortunately, fortunately, I guess, because it didn't hit anybody, but it landed in the Lake Ontario, real close to the shore, real close to Ohio. And so 3 hours before I took this image was the time of discovery by David Rankin at Tucson at the Catalina survey. And I got about an hour notice, and half hour after I took this image, it was in Lake Ontario. So so that's how good the discoveries are starting to get these days, which is pretty fun. And now I probably should have put this slide after that one 2 slides ago. Here's a successful meteorite hunt in Sudan. Pretty sure this photo is staged, but so here they are in Sudan, and there's some very significant meteorites. The figure at the bottom is kind of cool because it shows you where the really heavy stuff will fall here, and the really lighter stuff will fall earlier on along the path. And indeed, that's what they found with these fragments that are there. I mentioned Nick Moskovitz, my supervisor or hiring manager at Lowell. He set up a meteorite expedition based on this type of triangulation. One of them was at Lowell, and there were several others. So he thought he had a pretty good handle, and he organized a meteorite hunt that was near Gallup, New Mexico, that Jennifer and I went on, and he had good participation, like a dozen or so people. And here's some of them. This was right after a snow melt, real big snow melt, and that was problematic. So we didn't find one on the first day, and it was going to be Saturday and Sunday all day. We're going to be searching, like a line of people going along, trawling through the desert, through the high desert. I was happy to not go out on the second day because the first day, these are my boots. So they gain like 10 pounds every half hour to an hour, and that's what you're dealing with. And it was nice out there. It was quiet out on the reservation, but it was good to give this up. And I was happy to find that they didn't, well, kind of happy, sour grapes, happy that they didn't find one on Sunday. But Nick's going to keep trying. And these are, again, like everything I've spoken about, keeps getting better. So there's the topics. And I got through it in 54 minutes or something. So, which is rare that I don't go over. And finally, some movies and images of interest. So these are either images or movies that I took. I'll just go through real fast. Here's one that's only 4 Earth diameters away. So that's kind of fun. And these are moving really fast when they're that close. I keep mentioning JF and I have a real similar view of the hobby, I think. And we both took images of the same near Earth asteroid, and then he did the parallax calculation. We're at an almost identical latitude and much different longitudes, and he was able to determine from parallax the distance out to the asteroid within about 0.5% of its catalog or its predicted distance. Here's I like this galaxy field in Virgo, and just a insignificant main belt asteroid passing through. This one's pretty cool, Toro, which I observed for another group. And you can actually see the brightness changing as it rotates. Toro is also famous because a piece broke off of Toro. Okay, they know the orbit that well. And that's the one case of an asteroid hitting a person. This is in a lot of astronomy textbooks. And, she's a pretty good big target there. So, no. Stuff that I shouldn't say. No, I'm going to get letters. So here's the reason for this is that this is the dead comet Phaethon, which produces the Geminid meteors, and it's in an orbit that it does not come this close to the Earth very often. So I had to go out when it was 10th magnitude, 9th magnitude. It was very bright at this time. And speaking of moving asteroids, they'll put this one kind of shows it getting bright and faint as it rotates. You can kind of see that. has a real short rotation period of 3.5 hours. And this one's barely moving, yeah. So that's Vesta, which actually is the brightest, brighter than Ceres, the brightest of the asteroids. Naked eye object, if you know what you're doing, barely. And a much more recent one, I went out, there's a site of correlate, there's a site for everything. There's a site that tells you when asteroids are going to pass next to deep sky objects. So here's a beautiful cluster in Monoceros, NGC 2244. And using the Tycho software, you tell it to go find other asteroids. And fortunately, there were 2 others in the frame. There's one of them real faint up there. There's another one moving in that direction down here. These are both about 16th magnitude or 17th magnitude asteroids that I can't do photometry on. So it's kind of fun. And of course, what would the talk be without me promoting myself again? There's 4078 Polakis, and now the real challenging one, Mike Wiles did, because he's at a dark site and he knows what he's doing. This is going to be really hard to see, but at the top of each of these bars, you'll see a moving dot there, 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 not there, there. And so that asteroid was around 20th magnitude at the time. And no way, my backyard's 4.5 magnitudes above the natural level in Mill Southern. It's the dark site that it is. And Mike is out by the Chiricahuas. So that was great that he did this. And after a lot of working on the image, all the noise reduction, barely able to get it there. So that's my speech. Hopefully I win the White Dwarf Medal of Accomplishment for it. And if you have questions, and now's the time to fire away. We got 3.5 minutes, which is a relief because I probably can't answer them anyway. So, okay. So questions, comments? Oh, yeah.
Is this on? Okay, we'll give you applause first. Go ahead, clap.
Oh, all right.
Okay, so your buddy Jeff Gout is also online via Zoom. And he said, while you were giving your talk, his buddy, Rick, I don't know if I get this name right, Nick Nolenthius, has just had his binary due to occultations confirmed today.
Cool.
While you were talking.
Good.
So one more to the list.
Okay. I thought he was going to be hit by an asteroid, but okay. No, disappoint me. No, sorry. Yeah. Wait, let the microphone arrive. Yeah.
Are the current satellite programs that are going up with all of these thousands of satellites going up, is that causing any issues for you or concerns?
Somewhat. I absolutely despise all these programs, and it's not just Starlink. There will be tens of thousands further that are going to go up, and it's one of these things. I grew up next to Lake Michigan, and I watched things happen there that eventually we kind of said, why did we do that? You know, it was pollution, and that's what's going to happen here. It might be 10 or 20 years down the line, and sorry, there's probably Starlink customers in the audience, but that's just my view. But they don't hurt that much because they're only up for about an hour after astronomical twilight, and the direction that they're up to be illuminated is the direction of the sun. So you would have to be pointing in the west after sunset for these to be disturbing. And most people do their photometry and watch things go from east to west or near the meridian. So they're not a problem that way. They're going to be a problem for the great surveys like the Vera Rubin telescope that's going to come online. That'll be a problem. And they were really a problem when we had this great comet, you know, we just had a couple months ago, whose name for some reason is escaping me now, even October. What is? Yeah, that's why I remember. Yeah, Shuchinshan. Yeah, so we had that comet, which was just gorgeous, and it was in the morning twilight and then in the evening twilight. And when I'm looking through my SLR camera viewfinder live view, I'm watching these things constantly going across. And so, yeah, so I'm going to stop there because I could really lecture at this point. Yeah, and you don't need to hear that. Yeah, so, all right. So, questions, comments? Good. Man, I covered it. All right. Thank you.